Start up the camera. And we're live. Okay, so today we're going to talk about heating and cooling load estimating, which will start by just going through the different parts of a cooling load, a heating load, and then go more in detail of every part and piece. We might look at some heat transfer. We might spend some time on some weather data. No, we should do both of those. And then we'll hopefully wrap up with talking through kind of some rules of thumb and practical use for load estimating. Next time we'll talk more about equipment selection, block loads, diversity, and more system level load type stuff. My goal is to make this conversational or get some participation in here. So I'm typically, how I've done this in the past is I PowerPoint people to death and we look at pictures of stuff and I try not to read them. I'm going to try to use a whiteboard and draw a picture here, and then we'll use that picture to kind of go through how we think through heat loads as engineers, project managers, air conditioning professionals. Okay, so to start, I drew a building right here. So this is the first participation thing I want to, or activity. I want to go through what are the different things that provide, we're going to think cooling only, heat gain to the space.
Windows.
Windows, yes.
People.
That's an external heat gain. People, yeah. Actually, I got colors for this too. Okay, windows, I got people.
Lights. Equipment. Solar.
People, I heard lights. I heard equipment, this is a laptop, so I could use your imagination.
Transfer through the walls.
I heard solar, which is kind of windows, but the other part of solar is, so windows we also call fenestration, because it makes us sound really smart. And then walls would be part of opaque assemblies. There are other opaque assemblies we have.
Roof.
We got the roof. There's a piece of glass in this roof. We would call that a skylight. Yeah. Whoa. Skylight. Okay, we got people, lights, equipment. These are our interior loads. Then we got our envelope, which are walls, windows, roof. Is there anything else that might provide heat load to the space?
Floor load.
What was that?
Floor load.
Floor? Yeah. Maybe the ceiling, right? And some of these we'll talk through, they may be zero most of the time, or they might be small enough that we'll ignore them. Ceiling
Would you
could be
consider
interesting.
infiltration different from?
Yep, infiltration is on the list. Yeah, to do that, let's draw a door on this thing. So infiltration would be buildings are not perfectly separate from the outdoors. When you open a door, hot air comes in. Ideally, well, we'll get to infiltration when we get there, but leaking of the building, we've got doors, which are seen which are a lot of the time ignored and used as part of walls, but are a separate function. And actually, I'm going to draw infiltration not here, because this is different. This is an exterior wall, and this is an interior wall or a partition. So if there's a temperature difference between partitions, we have a partition load. That green just really stings the eyes. Anything else? We're going to overly simplify this, because we're going to get to it more next week, but there's parts of the system that need to be accounted for in the load. So the biggest of which is outside air, typically, but fan heat, reheat, duct leakage, that type of stuff. As we go through these items, I guess important to understand that we make a lot of assumptions for this, and there's safety factors that can be applied here, that can be applied at the system level, and so it's important for us to know where our safety factors are. That way we don't oversize or undersize equipment by adding safety factor on safety factor. So if you start to get really worried about things that are commonly ignored, like partition heat transfer, you're going to start to oversize equipment. Because typically doors, partitions, infiltration, ceilings are not part of our room load calc. Okay, anything else I missed? Any questions about that for cooling? Yes?
What are we considering partitions again? Since we already have the
Yep.
ceiling and
So a wall is something between the conditioned space and the outdoors. A partition is an interior wall that might be conditioned. The only time we really account for them is if it's a wall between a conditioned and an unconditioned space, and even then, they're not a huge part of the load. Okay, so now,
Did you talk about plug loads?
plug loads would fall under equipment, but yeah. So now we're gonna go through each more, but that's good. This equipment could be lots of different things. Yeah, that's a laptop. Looks like a smiley face, but this is heat coming off it.
Where's the hot tub?
Hot tub is a very important equipment load because it's not only sensible, but it's also latent, right? And we're not going to talk about hot tub right now. So now we're going to take these, and I've put them in 3 different buckets, or 4. But usually we think about them in buckets of internal, which are people lights equipment, envelope, which is like your walls, your windows, your roof, and then other lesser things like infiltration and system. So let's go through one by one, and we're going to use this handout. Before I reference it. Last call. Does anybody need another one? I have one more. Okay. This is an example of basis of design. We use basis of design in engineering to kind of explain our assumptions and why we do what we do. One of my favorite ways to use the basis of design is to explain how we're sizing our equipment, especially on big projects. Little assumptions can change the sizing a lot, and so we want to be clear what type of things we're using to size it. Let's go to the last page of the BOD, which is going to be the 5th page. And here we have a table for occupant, equipment, and lighting heat gain criteria. So which one of these markers works best? Let's go here. So people, how do we come up with a heat load for people?
Should look at the activities that they're doing.
Yep, activity level. So there's two things. There's the activity level, which we have a table for. So, and ASHRAE is full of people that think about these things and test these things and have given us a literary source that we can reference and design off of and say, hey, we're following industry standard. So that's what this comes from. This is an ASHRAE table from somewhere. I don't know where. But it's referenced a lot when we talk about people. If you are in a gym on a treadmill, you're pumping out a lot more BTUs and a lot more sweat, latent load, than if you're in an office sitting. The one we use the most in this table, any guesses?
Stationary work.
Number two would be good. And number two is often seen as 250, 200 instead of 245, 205. So these numbers are sometimes a little different. So usually when we use office work, we use 250 sensible and 200 latent. So in most of what we do, we use office work. The only time we do something different might be a lab where they're gowned up, or like a gym. So that's the activity level, and then how do we turn the activity level into BTUs? We count the number of people. And how we do that is we usually do like 100 square foot per person for an office, or we put 1 or 2 people in an office depending how many chairs there are. In a room like this, we might count the chairs. And then we multiply that by 200 to get the sensible load, and we multiply it by 250 to get the latent load. Does that make sense for people? Okay. There's a lot of assumptions there. At a room level, we usually want to be, and I'm going to say this for everything, at a room level, we usually are looking for a max. As we start to add up all the rooms, we're quickly going to find out we might have a floor that we're counting like 100 people, but we know only 50 people are going to be in that floor at a time. So we might take some diversity as we go to bigger components. But that's how we get through people. Okay, what about lights? I'm going to write this down so I have something to do.
You can directly take the wattage output.
Yeah. So we could look at the electrical plans, and we could look at the schedules, and I'm not even going to describe this right because I've never done it, but we could get the actual lighting and use that for a space. Generally what we do is use some sort of watts per square foot that is either equal to the code allowance for that space or something bigger. Thought being it could change, and lights are generally not a huge part of the load. So a very typical normal office building would be like 1 watt a square foot. That has changed a lot in the last 20 and even more in the last 40 years, because LED lights use far less energy than fluorescent or incandescent. Those used to be 2 watts a square foot plus. And actually, Mike Gallagher has written articles on how it's changed like our idea of reheat and just interior loads, but we won't go into that right now. That could be a future talk. Lights fall under the stuff that's on the switch. They also could be like desk lights. You don't see a lot of those, but a lot of times people will have like individual lights at their desk. The other discussion we think about is the heat from this light doesn't just come out and into the room, it also has a ballast behind it. So a certain percentage of that heat goes to the plenum, and there's a difference in how we treat the room. The room we have to condition by blowing cold air. The plenum is picked up in the return air. If we're really getting into the load, we're gonna differentiate that. Or a software will differentiate that. If we're doing a spreadsheet calculation, it's not gonna be that big of a deal. But just know that it's something engineers like to talk about, and that's part of the reason I'm here, is to talk about things I like to talk about. So you guys might someday like to talk about it. So. Okay, and then what's the last thing that's an internal load? Equipment. So what's an example of heat producing equipment? What's that? Or transformer. I think that was kind of whispered, but yes, that's good. So electrical rooms are rooms where we're typically going to add up the transformers and use something to come up with a heat load. Rule of thumb is usually 3% of the kVA. It's going to give you about the heat load for that. New transformers are much more efficient than that, but it varies. So you should hem and haw about it for a while, or ask me, or ask. Also, you should make your engineer come up with that, so you don't have to, right? But this is a good way to check this type of thing. So electrical rooms have a lot of those. Transformers can be in the space too. Computers, we usually have some allowance for computers. Those have gotten much more efficient too over time, though they might have bigger power supplies. Those power supplies don't run as hot and as fast as they used to. Depending what you're doing. And there's data published on that. What else? What other type of equipment is interesting? Cell phones.
No.
Cell phones we kind of ignore. Might be a plug load. Or so Chad brought up a plug load. That's something that might go into an outlet. So charging that cell phone might take some heat.
What about like individual space heaters?
Yep, that's a load. And that's not something we're gonna pretend actually exists. Because when we design air conditioning, you shouldn't need individual space heaters, because we're gonna mix the space so well and reheat it when you need it. And you're gonna plug that when the fire department comes, so is it really there if it's not there when the fire department comes? I don't know. But that would be under the plug load. There's two other specific spaces I'm thinking of where equipment's a big deal.
Server rooms.
Okay, 3, yep, server rooms, kind of like IT. And server room, like,
That's its own
it's its own beast.
Yeah.
Kitchen.
Copiers, good, yep. That's typical office equipment, that would be said different. You just say kitchen?
I was
You said
thinking
kitchen?
equipment, yeah.
So kitchen has like its own load calc class of its own. We have spreadsheets for how to deal with that. You have a lot of things that generate a lot of heat, but like aren't always on. So there's like utilization factors, there's a lot of heat that goes into the hood, so we like to think about those, or you should see something very different in the kitchen. And then clean rooms or labs usually have some sort of equipment, and usually things we don't understand. I guess one of the things I'll point out for kitchens, labs, servers, is we can make assumptions, and we've done a lot of these type of things, so we have a general idea for what they need, but usually we're looking for an engineering direction from a lab planner, a kitchen planner, or an IT person to give us those heat loads. That's not something that's like intuitive to an HVAC engineer and ranges a lot. So there's a lot of, we experience a lot, oh, this is this type of lab, like you're an engineer, you know what that load is, and we'll be like, oh yeah, we know. But no, someone needs to give us point of connections for hoods, which is not a load thing. Someone needs to explain their lab process enough so that we can do heat loads on it. Important thing is servers, kitchens, clean rooms, labs. That's the equipment typically drives those loads. Also, air changes may drive those loads, which we're not getting into today, but maybe we'll take a turn that way. I think Gallagher was big into ranting wherever we wanted to go as a group, so I'll do that too, as long as I don't run completely out of time, which I don't think I will. So, okay, that's our internal loads. I guess the other thing is when you get a lot of equipment, depending how it runs, there could be, so server room's a perfect example of this. You may have a connected load of 20 kW per rack, and it might run at 2 kW. You could also have 20 kW per rack, and it might run at 20 kW. So those are things we want to be clear with our owners or coordinate with our other consultants to make sure we're sizing our air conditioning appropriately. The most conservative way to deal with the server room is just size the cooling to the power going in the room, but then you're usually way oversizing the equipment. That's changing because servers take a lot more power now, but which is really exciting. But I still think most of our servers have a connected load above 10 kW per rack and run below 2 kW per rack. So. Okay, so that's internal. Put this on here. I'm gonna have to erase it at some point. Okay, so now let's do envelope. This is where we get into weather data. What order do we want to do this in? Okay, first let's talk about, when we think through loads, the geometry is important. So the area of the wall or the area of the window that interacts with the outdoors is how we come up with our load. The temperatures are important. So the temperature outside, which we'll talk about some weather data in a little bit, and the temperature inside is going to drive our load. And then whether we are north facing, south facing, east, west, that's going to affect our load. Why does it matter which way our wall is facing? And Gallagher's probably already talked about this, huh? Yeah.
How the sun rises.
Yes. So the sun rises in the
East.
I feel like this is a western thing, right? And then sets in the west. So in the morning, the eastern exposures are going to get more sun. In the afternoon, the western exposures are going to get more sun. And the south is going to see the sun all day, because the sun kind of goes across the south face of your building. And the north, we often treat as just shaded, or we use the north wall as like a placeholder as a shaded assembly, because the north doesn't get direct sunlight, typically, because it's shaded by the rest of the building. Okay, let's talk weather data. I give you a table. So on the next page, so we have, this is from the 2025 Joe Dependencies. So this is published by the California Energy Commission. It's a reproduction, I think, of the ASHRAE fundamentals weather data, though it gives it in different terms. So I'm not sure exactly how that happens or where it comes from, because ASHRAE has weather data that looks like this, which is way too small for you to even know what I'm looking at. And it's a little bit different. I tend to like to reference this when I put together a BOD because it's a literary source put out by the Energy Commission, and kind of gives it, and ASHRAE would be good too. So on this, got a list of things I'm going to point out. We have a list of columns. So first we have a city, a latitude and elevation and longitude, which corresponds to a weather station that gathers that data. when we design a building, we usually have like an interactive map where we can look at where this building is in comparison to the weather data around it. And based on our knowledge of the area, or by picking something that's closest, or by being directed by an owner, we use weather data that's most representative for that space, because we don't have weather data for every address. So places like Los Angeles, you can see we have Los Angeles Airport, which is more close to El Segundo, more coastal. And then you have Los Angeles CO, County, maybe? I don't know. But that's more inland, and that's typically warmer. And if you look at ASHRAE, there's actually 3 different weather stations in Los Angeles. Here's a little bit of a rant. If you go to SoCal Edison, they have tons of weather stations, and they've been tracking the weather data even more than ASHRAE because they're very nervous about fires. And those values are not published for political reasons, but they have 340 stations where this probably has like 200. So there's, and then you have like the NOAA data, the NOOAA. It's something like that you pull weather data from that'll also give this type of data. Point being, we need a literary standard to tell our customers how hot we're designing the building to work at. Okay, so keep going across the columns. I've got 0.1, 0.5%, 1%, and 2% cooling, dry bulb, and wet bulb temperatures. Did Mike do a spiel about what dry bulb and wet bulb temperatures are? We're all good on that?
Yes.
Okay. Probably got a sling psychometer. Good. I didn't bring mine. So does anybody know what those percentages mean?
What percent of, I guess, time during the year, or
Mhm.
which percent of days would we typically look at? Do you have those temperature conditions?
Yep, so
Those
the
design
number
days?
of hours
Yeah.
where the temperature is at or above that temperature for the weather data. There is a term for it. No, I think that's good. So it's percentage. So to give you a feel for that, there's 8,760 hours in a year. For the 0.4% data, that means this area is going to see that temperature for 35 hours. And that could be, that's probably not 35 hours in a row. That's probably hitting it and then going back down. So there's 2 tells to weather data. One, this is the absolute worst. We're not going to get there very often. Okay, and that's kind of true. Most of our buildings, do they run at peak load all the time? No, they usually run at 20 to 50% of load. And that's not just weather data. They're not fully occupied all the time. We don't have all the lights on all the time. Usage varies. So that's one side. Get aggressive, cut your loads. The other side is this weather data. The world is getting hotter, I guess is what I'll say. Or we see more than 37 hours above some of these wet bulb temperatures and above these sensible values. So the one we love to rant about as a company is, no, this one, it's not on here. If you look at, no, it is on here. If you go to the design wet bulb column, so after cooling, you go to the 0.1% design wet bulb for Los Angeles County. The 0.1% is 72. And the wet bulb temperature in LA has been much higher than 72 these past 2 weeks. So anyone who has facilities that are dehumidifying, they're hurting because they're probably not designed to above 72. What else is interesting about, so just something to keep in mind. Weather's always changing. It's always getting hotter, it's always getting colder. We're gonna complain either way. We need to anticipate what our customers need. For a commercial office building, it probably doesn't matter if it goes a little bit above these ranges. For a pharmaceutical business where they have to shut down a line if it goes above the humidity, then we would add adders to some of these design temperatures. Like we'd add a few degrees one way or another. But before I get into that, does anybody know where we use the 0.1% versus the 0.5, 1, and 2%? Like how do we decide what to use? Good guess. If we went to the desert, we'd pick a city in the desert and the weather would go up.
Each guy or anything like that?
Yeah. So critical applications, you're a lot. So engineering judgment, if it's critical, you want to use the most stringent design because it's got to stay up. So code allows healthcare to use the 0.1% data. Code also technically doesn't allow office buildings to use the 0.1% data, which is kind of interesting, and it's kind of a bit of an ethical dilemma. So in theory, if you have an office building, you can't design above the 0.5% cooling data. From a practical standpoint, we are not going to short our customers on air conditioning. The reality is there's a lot of safety factors in these loads. How something like that gets enforced is a little silly, but engineers love to rant about how the weather data is not accurate. We're required by code to use the weather data. Like, that's why my building's not working. That's a really lame excuse. Don't ever use that. But it's a fun conversation if you run into some ASHRAE guys. Maybe don't bring that up either. Okay, so critical 0.1%. Other buildings, there's a ratchet. You can use anywhere from 0.5 to 2%, depending how critical it is. Design wet bulb is how we design towers. We talked about towers in here. Cooling towers use evaporative cooling, so the limit on what your tower can hit is determined by the wet bulb. We will talk about heating later, but there's heating temp on here. There's also other weather data that's not in this that will give you how dry it gets, like how many grains of humidity you see in the winter, and we use that to size humidifiers. The peak cooling temperature may not correspond with the highest enthalpy. So out at Eisenhower, while we have 117 degree days at 74 wet bulb and higher, and Ron and Sam and David will tell you how hot it is out there right now. Sometimes the worst days are when it's raining at 100 degrees and we've got 100 degrees outside and like a 79 degree wet bulb. In Southern California, besides Eisenhower and the monsoon season, generally the peak load or the peak day is also the peak enthalpy. South might have the same thing, or like Georgia, Atlanta, they have really hot, moist days. Generally, we design mostly to the sensible and don't worry too much about the length. But that's another factor to think about, is how you deal with the humid days. Okay, we're gonna come back to this for heating, but right now we're not talking about heating. And we don't talk about heating a lot in the market, but we will today, so get excited. One other thing that comes from here, ambient temperature, and this is less, it's kind of getting off the load thing. So we care about the ambient temperature or the outside air temperature because we suck in outside air and have to cool that down when it goes in the building. That is sometimes handled differently with our heat rejection piece of equipment. So for towers, we have a wet bulb temperature. For a dry cooler or a condensing unit, we will typically either use the cooling dry bulb or we will add some factor to the cooling dry bulb for heat island effect. So for Los Angeles, if you look at the 0.5% for Los Angeles County, or CO, whatever it's for, you'll see 92. Usually we're designing outdoor equipment for at least 95. To go above that wouldn't be unheard of either. You could make a case for setting it the same as that. It's just another place we have safety factor that kind of gets more to equipment selection, so spoiler for next week, but is in this spot.
You mentioned a heat island.
Yes.
That's basically like the inability for a piece of equipment to move hot air away from itself.
Yeah.
Okay.
Or heat island, I guess I'm using a term I probably shouldn't. Heat island is associated with if you put a bunch of buildings in a space or a bunch of hardscape and equipment, you're going to have a localized raised temperature. Same thing with a roof. While you might have a weather beacon that gets 92 in an area, just because of the nature of a roof and all the equipment kind of in the same area, it's probably hotter. I don't have a good literary way to deal with the offset between that weather data and the roof, but it's another place that engineers carry safety factor. So that's probably a good way to describe it, right? Yeah. So I wouldn't describe it the way you described it because we're always going to lay out equipment so that it breathes fine. Yeah.
Flow, right.
That's a separate equipment layout discussion, which we can totally break too, or we can account for it, even better. Yeah. Okay. Let's see how we're going. Oh yeah, we're good. Okay, so we got a bunch of temperatures. How do we apply that to our envelope? And how do we want to break? I'm going to break the envelope into. We're going to look at opaque assemblies. And we are going to look at, I got a picture of a wall somewhere, not in the front, in the back. I think it's the last page. And we're going to talk conduction because it's the easiest one. So Q equals UA delta T. This is BTUH, so BTUs is what we're trying to get in load. What's the U factor?
Universal coefficient, or I think that's
Some sort of coefficient.
It's the opposite of resistance.
Yeah, okay, well, that's good. U equals 1 over R. We'll use that later. It's some sort of
Thermal
property.
Conductance or whatever.
Yep. So it's the heat transfer coefficient. It's in BTUs per hour per foot squared per degrees F. But the U factor and R factors are how you tell how much something insulates. So if it's got a high R value, think bad insulation is usually like R13 between the walls. When we talk roofs, we're usually talking a built up R30 roof or a BAT R19 below. And then U factors are the inverse of that. So they're more along the lines of like 0.1 to 0.46, which we'll get a little more specific. But some value of the wall or the window. And then the A is, it's a geometry thing. Area. And delta T is the difference between the outside and the inside. So for LA, if we're using we said it was 92? Minus 75. If our set point is 75. Typically, 75 is kind of the standard setting for air conditioning in our calcs. Or what's, we've got like, and this isn't even one of those equations, we have like 4 equations that we use a lot in our industry, but the other one where we see delta T is 1.08 CFM delta T. People using 1.08 CFM delta T or 1.1, or does that sound familiar? Yeah. Typically this is assumed to be 20. And this is different than what we're talking about, but this is the difference between the room set point and the supplier temperature. We're going to come back to this later, because if you mess with this and you mess with this, or you mess with this, you mess with the load. Right? So if it gets hotter outside, it matters. You blow colder, warmer air, it matters. You jam the thermostat down, it matters. It all affects the load up or down. It all goes up in everything I said. But if you do the opposite, it should go down. Okay, so why are we talking about this equation? This is the relationship that walls, or this is how we get the load associated with walls. And how do we come up with these U factors? Yeah, that's not real. So the way we come up with these U factors is we need to understand how the building's constructed. If it's a new building, it's great because we got an architect who's like really excited about how the building's constructed and is drawing something, and we're going to be talking back and forth with them about how much bad insulation they're going to have, how much continuous insulation, are they using stucco, are they using, what else, whatever you put on the outside of buildings, plywood, I don't know, not plywood, metal cladding, and so that's, it's interesting because we get really involved in it because we have to air condition it, but it also means we have to kind of understand how buildings are built, because architects really just want to build their building and they don't want to talk air conditioning, they don't want to talk energy code. Okay, so let's talk energy code for a minute here. One of the energy code regulates how the level of insulation, walls, windows, roofs need to be. And because we think about that a lot for load calculations, we're generally the people that create the envelope compliance for the architect. And so we talk about this stuff a lot when it comes to new buildings. Which puts us in a weird place because we don't build the walls, we just have opinions on how much insulation it needs. The architect and the general contractor are really going to be the ones building it. So how do we do that? Sorry, we're getting there. No, let's stay on energy code for a minute. So energy code is kind of like load calculations. We think about similar things, but load calculations, we're kind of taking the worst case to size a piece of equipment for a point in time. Energy code, we're trying to get generally what's happening throughout the year, and we're going to run a year-long simulation to come up with how we can minimize energy over this time without missing the set point by too many hours. So they're not the same. They generally use different programs, or most engineers use something for their load calcs and use something different for their energy compliance. Though you could use the same thing, we just don't trust them the same. And you play a lot more games with the energy code compliance. We'll leave that there. Okay, so how we come up with U values, you can build them in software, you can look them up in tables. How we like to do it generally is look them up in tables. So the California Energy Commission has a joint appendix that has every type of assembly in it, where they have tested different materials and iterated. A lot of it's calculated, but a lot of it's tested for different assemblies. So what we'll do to do our load calculations is we'll look for something close to it, get the value from here, and then either add up those values or adjust those values to account for the actual situation. So this table right here is for a metal framed wall. If you can see different stud spacing, so 16 inches on center, 24 inches on center, right? We kind of get how a metal frame wall works. You've either got 16 or you got 24. That look like 24? Yeah. You got the frame sizing, so it could be 2x4s, 2x6s, 2x8s. And then there's different cavity R value insulation. So think the pink or the rock wool, or that's typically your cavity insulation, the stuff that goes between the studs. And then if you go to the right, that R0, R2, R4, R5, 6, 7, 8, that's continuous insulation. And what that is, so we got our studs, we got that. Our continuous insulation is something that goes in front of the studs, either on the outside or the inside, and does not have these studs going through them. What is the difference between continuous, and there's an obvious answer, but I'm not going for the obvious answer, the difference between continuous insulation and cavity insulation, besides one goes between studs and one is continuous. Is one better than the other from the thing that matters, heat load perspective? Yes.
I would think,
Yeah. That's the safe answer.
More
Continuous.
surface area for heat transfer?
Yeah. Say it again?
Oh, sorry. More surface area for heat transfer?
Explain.
Like, for, I don't know, for like
You-
insulate, like, insulation.
Yeah.
No, never mind. You wanna
Okay.
keep, you wanna keep these.
They're different. So you're right. This has more surface area of insulation than the bat does, because the bat is interrupted with metal framing. So here's another like engineering thing that we're passionate about, is the concept of thermal bridging or thermal break. When we and it counts for this in this table, but I'm going to use another equation because we love equations here. When we add up, and this is going to be kind of like electrical, when we add up this, like this and this, that's in series. So that's going to be R1 plus R2 equals R total. You just add them together. When we add these up, they're in parallel, right? Or this can be seen as, you think more like an electrician, like this. And thermally, this and this, and it's not exactly in parallel because this isn't straight. But if this is R19, and this is R19, and this metal break is like R.5, right, or something very low, this is going to be R19, and this combined assembly is going to be something lower because of the thermal bridging of the stud. I'm sorry, how this worked is 1 over R1 plus 1 over R2 equals 1 over R total. And there's an easier way to think about that with the U value. U equals, and no, it's not that, it's A total. A total. Or it's going to be the same as U1, A1 plus U2, A2 over A total. Which I thought of doing an example with this, but you're probably never going to use it. But it is an important concept. And it comes up in the field. So this R19 is not an R19 assembly because the heat will go through this metal, making this something less. If you took a metal pan, this isn't a good example. What's a good example? I don't know. If you took a metal pan and put some insulation and put heat on it, you still won't touch the metal of the metal pan. The insulation is not stopping the heat from going up through the pan. Because the heat will go through the thermal bridge. This creates a thermal break between the stud and the rest of the building. So we're going to learn how to use this table and also see how that works in practice. So if we look up a 16-inch on center 2x4 metal stud wall with no continuous insulation and R13 cavity insulation, what's the U factor? And the U factors are all the numbers in here.
Repeat.
R13 cavity insulation, 2x4 framing, 16 inches on center, no continuous insulation. So we're gonna be 1, 2. Oh, and what's nice is they set this up like Battleship. You've got 1 through 30 in the gray, and you've got A through K in the gray. You see how the rows have 1 through 30 and the columns are A through K? So I can tell you the answer, like Battleship, so I can say the answer is A4. You're not going to say hit or miss, you could read the U value, which is 0.217. Does that make sense?
Yes.
Okay. So that's an R13 cavity insulation assembly. So that's a U factor of 0.217. That'd be like an R value of 5. We're kind of rounding. Let's do something similar. So if we use R12 continuous and do no cavity insulation, what would our Battleship coordinates be? I've never used this before, but now I'm going to call it that from here on out. So that'd be row 1. And what column would we be looking at for R12 insulation? Be a letter. I, yeah. So 1I, and that U factor would be 0.071. So same level of R value, but because it's continuous, you get a performance. That assembly R value would be the same as 1 over 0.07. I don't know, that's a lot. It's more than 10. So just an example of how important thermal break is for performance, and I bring this up because this comes up in the field and is confused. We put together Title 24 forms, we put together load calcs and show on our plans, hey, you need R19 continuous insulation, and the general contractor will go out and be like, great, we need R19 insulation, they'll buy R19 bat, put it in the studs, and that's not the same thing. I should blame architects, because we deal more with architects. Architects will do the same thing. We'll say, hey, you need R19 continuous insulation, and they'll put it between the studs. Also, the detail for building this, and like putting the clips on here and pinning this, is a lot more work than what was done 20 years ago. It's just a harder detail to build. I think it's much more common in new construction now than it was even 10 years ago, but it's still kind of a new thing to our industry.
Question.
Yes?
Do the inspectors know this when they go out there to take a look at it? Or,
Sometimes.
or
yeah.
will they go out there and look at it and be like, this is a 14, this is not a 19?
It depends on the city. So City of Irvine might notice that. Um,
Cause what if they don't know about this and then they go out there and they're like, wait a minute, this is
Yeah.
not 19, is this 19 here? And they make you break it down.
a lot of things that we do in engineering, enforcement varies. And it's a risk proposition. I mean, the other reason we're tied to this is not only is it an enforcement thing, but like if our unit is undersized because the envelope's not installed correctly, like that makes us look bad too. So that's why we're passionate about it. So can an inspector tell? Yeah. And have we had inspectors bring that up? I guess, and that reminds me of another way. So we use tables. These tables are the same thing Energy Pro would use, which is the big Title 24 compliance calculator, which is how we generate our forms, so the inspector can check those things. We piece together assemblies. So if we have a metal framed wall in front of a concrete wall, we'll add them up in series. And it would kind of push these tables together. There are more advanced ways to calculate U values or U factors, and more so on the Windows side, that can sometimes give us credits, that if it's a big enough project, we can go to like a specific consultant to help with that. Or a lot of times we'll work with the window, like the glazing vendor, to get actual values. Because these are assumptions, these are available, these are agreed upon, but like all things, there's some guy doing, it's not a CFD, but has huge software and like thinks about these things day in, day out. And so there's different pathways to compliance sometimes. Where I've seen that happen the most is if we're doing, blanking on the name, like a spandrel system, or where the whole building is made of glass, but like we fill it in with spandrel. Which now I need to explain what spandrel is. So a lot of these big skyscrapers look like a big glass wall, and you have areas where they're just glass directly to the inside, but then you have areas where we kind of soften out the inside, the opaque assemblies, and we call those opaque assemblies spandrel. Is that a good description of spandrel? Does that sound right? I think so. So it's a continuous a continuous piece of glass, and we'll build up insulation in walls below a certain height and above a certain height. There's a lot of complicated calculations you can do to calculate that assembly, and we've used that on some of the high rises we've done in Culver City to be more aggressive with our assembly type and meet code. Which is going to be my segue to Windows, I think. Oh, and I got tons of time too. You guys usually go to 1, right? Okay. I'll try to be done by 1. Okay, any questions about this before I go on from walls? This exists for roofs, this exists for concrete walls, this exists for wood walls, you name it. It exists for spandrel, it exists for, that might be it. Oh, skylights. There's like 400 pages to this thing. Everybody should read it before next week. Okay, so that's opaque assemblies. We looked at some equations. Okay, windows are similar, except what's different about windows? You can see through them, they let in the sun. So this is conduction for opaque assemblies. They're only going to see conduction, whereas windows, yes?
I had a question, it just kind of just popped up.
Yep.
Like with green roofs and stuff,
Yep.
does that change, the R values?
When you say green roofs, so you're talking
Like
like
when they have
cool roofs, or you're talking about ground grass on your roof?
like the, I
Like,
don't know.
and I mean actual grass.
Yeah, no, when I worked in in the state of Washington, like they
Yeah.
had, I don't know, some sort of like, incentive,
Mm-hmm.
right?
Yep.
To like lead approve or whatnot.
Yep.
With like having, because with the green roof, like if say you're facing the sun and you're reflecting off the window,
Yep.
it minimizes like right on like a outdoor patio sort of area.
Mm-hmm.
I don't know. I'm kind of just rambling.
So with roofs, you have same as a wall, just like this, right? But it's different because there is code requirements for the color of the roof, and cool roofs have a certain SRI, which I don't remember. Solar reflective index. Oh, I do remember what it stands for. Yeah. So there's requirements that color be a certain color so that it reflects, not absorbs, because if it absorbs, we got a condition that air, costs us money, costs us energy. And then they also have a requirement for insulation value, which is what we were going through. I do not think that exists for walls, which I've never thought about till right now. But roofs, we talk about it all the time. That's been like a lead thing, and that's a code thing, and that's it's called a cool roof. It's typically what it's called. It might be called the green roof too. I mean, the other thing is some of these green buildings will actually create a like landscape on their buildings, and that's much more complicated. And I don't want to think about that from a load standpoint. It's probably good. It's probably a good insulator to have dirt and grass on your roof.
I've heard it discussed that one of the issues you can run to that you have to be mindful about when you have a reflective roof like that is that you can basically create a bunch of reflection of the light right into your equipment that's then adding load onto
Yeah.
your equipment.
Never thought about that,
process.
but yeah.
But yeah.
Goes back to the ambient temperature, right?
Yeah.
You're gonna have
There's
higher
no light.
heat up there.
Yeah.
And hardscape does that too, right? You put a bunch of concrete in around the building, it's gonna be warmer than having a tree or having something easier on the eyes. Because we'd all rather sit in the grass than sit on the asphalt, which is not reflective, but really hot. So concrete's more reflective, yeah. That works better for that example. Okay. Let's keep moving. We're going windows. We'll use a big word for it. We're going to talk fenestration assemblies. I guess the other thing I probably should have pointed out, the exterior stuff, all of the interior things, the people lights equipment can be done in a spreadsheet, and it's pretty straightforward, or it's a bunch of assumptions. The walls and the windows and the weather data, that's where we rely on software and like programs, and there's like 80 different ways to deal with that. So that's where it gets really exciting. So sorry, we're already halfway through the exciting part. With no warning, we're just going for it. Okay, so windows have the same conduction, but they also have solar heat gain. I don't have anything in my pocket for windows. I think if you go to the BOD, go to the second page of the BOD. On the top there you can see a spandrel. So we pull these right out of the California Energy Code appendices. You can see a roof right there. And this is our way of looking at the architect's details and saying, hey, this is what we think you're doing. I love using these because 90% of the time when I do this in front of them, the architect will know. Probably 40% of the time they look at it and are like, that's not what we're doing something a little different. Probably 60% of the time they just don't respond to me, but that lets me make my assumptions and move on. somewhere in here I cover windows. Here we go, page 3. So when we talk through windows, we list a solar heat gain coefficient and a U value. So U value, we know how to deal with those, right? We got our UA delta T. Solar heat gain coefficient give us our they're a way to calculate the radiation and the heat from the sunlight, and that's a big deal. Or we all kind of get that. A lot of what we do in the air conditioning world is driven by windows. The lobbies, the cool-looking spaces create a lot of air conditioning demand, which is great because we love installing air conditioning. Low U values are better performing. Low solar heat gain coefficients are better performing too. So there's, with windows, the worst type of window is a single pane clear window. And that's gonna have, and that's not that uncommon for something built pre-90s on a lot of these existing buildings. That's gonna have a U value of like 1 to 1.2. And that's gonna have a solar heat gain coefficient as bad as like 0.82. How do we make those better? So if that's the worst type of glass, what would be a better performing type of glass? Double pane, yep. So double pane glass is pretty much the standard now. We spend a lot of time, so really cool glass is single pane still, to use a technical term. Let me make it technical. Architecturally significant glass is, that looks neat, wants to be single pane a lot of the time. So sometimes we will provide efficiency measures in other parts of the building to offset poor performing lobbies to get like curved single pane glass. But double pane will take our U value from something like 1 and get it to half or below. The other way we mess with those double pane windows is like there's different types of gas they put in there, like argon, and I can't think of any more, but but they put different types of gas between that and gaskets, and the way they engineer that is interesting. We're just looking for the solar heat gain coefficient on that cut sheet. And when I say solar heat gain coefficient, I was talking U value. Yeah. So how do we get the solar heat gain coefficient better?
I was gonna say you can also put on special like glazing slash like coatings to the glasses windows.
Yep. Which generally changes the color. So
It's
Yeah.
like tinting or
Yeah.
something, right?
so usually it's like a blue or a brown. Gone are the days where you see huge facades that are clear. You're usually seeing like a blue or, and the reason we do that is that lowers the solar heat gain coefficient, that reflects some of that sunlight out instead of sucking it into the building, makes us more energy efficient, helps us keep our load low. And then there's another term, relative solar heat gain coefficient. The other way we can deal with windows is we shade them. So if that window doesn't have direct sunlight in it, the load is going to go down. And so you can have clearer windows if you provide some sort of overhang, some sort of tree. Not really. From if it's there forever standpoint, yes, trees can shade, but trees don't stay always. They get cut down and they get trimmed. So usually we don't account for trees. Also, day one trees are not trees. They usually get VA'd into smaller and smaller trees because they'll grow in 10 years. But it's a shading. From a calculation standpoint, we could do it. Usually a canopy, another building, that's something we factor in. So remember, single pane, like a U value of 1 or 1.2, and solar heat gain coefficient 0.8-ish. The current prescriptive code requirements are closer to a U value of 0.47 and a relative solar heat gain coefficient of 0.31. So we've cut those in half, and they might even be worse than that. That's just what we did for a project. I think they're actually worse for that. That was an alterations project that we did with Gensler a few months ago. So, but they're like half of what they were. Okay, who cares? Let's go compliance. It varies widely, and it's hard to tell with existing buildings what type of glass you have if we don't have something that tells us. So just know when we're looking at an existing building and we're trying to cut the load or we're trying to do something different in the design, it's not an easy thing to do if we're not selecting that glass. Also, building envelopes don't get better over time. So yes, some engineers way oversize stuff, and if we have data that proves it to us, let's not go back with the same size. Let's make a good case to right size the equipment, but we need to have the data, because generally we don't want to change what's already working on a building. I'm doing this in the context of windows, but existing windows can be hard to quantify. Yes?
When you're doing like retrofit work, right?
Yeah.
Tenant improvement or whatnot,
Which is a lot of what we do.
and you're increasing your heating sources in the space, either with more equipment,
More people?
more people.
Yep.
And you need supplemental cooling.
Yep.
But your infrastructure is like already set in place. What are some like ways you get additional cooling with a retrofit?
New equipment. You could add a fan coil. Maybe you can run your supplier temperature cooler. I don't know. Maybe we'll get more into that next week. I do want to segue into this topic a little bit. Let me come back to that, because that's kind of off topic from what we're talking about today, but it's kind of related to how we practically size room airflows, which we might talk about more next time, because I'm not going to talk longer than 10 more minutes, even if I run out of material. No, it's a good question. It's just not. What we want to talk about today is how we quantify that load. How we fix that, that's the next guy's problem. Like Brian next Friday. We'll talk about that. Future Brian. Okay, now we just got to check some of these other things off the list. Any questions about Windows? What are other things you've heard about Windows? Any?
Yeah, I would say operable versus not operable.
Oh, yeah. Operable windows have lower U-value requirements, just because it's harder to get those U-value requirements. Like the way the framing works is more difficult. Windows deal with thermal bridging in the same way walls do, right? They're not just glass; they have aluminum frames or wood frames or whatever. There's also really advanced software in Windows to calculate things. We also don't do that. This is part of all my sessions is going to be like disclaimers of what mechanical engineers do and don't do. We get U values from window manufacturers. We don't calculate them ourselves typically. And that's a common misconception. Yes?
What about like stained glass windows in churches and stuff? Does that have any effect on?
Those are generally very poorly performing windows. I haven't done a new one. Okay. Yeah, I think how you would deal with a stained glass window in a church now is you'd have to have two windows. You'd have to have a double assembly. Something that gives you that look that you want, and something that gives you the thermal performance. Because my understanding of having broken one as a kid, they're not very good thermal performing windows. beautiful, but I think if you wanted to get a well-performing envelope, you'd want to have some sort of double assembly. They're also not as popular as they were
This is
40 years ago.
maybe
but
too
yeah.
off topic.
But now we're getting into church architecture, which we can write down.
Arguably, if the window's like high up,
Mhm.
could you say that like the loads in a stratified space that's makes it not necessarily affect your actual occupied zone?
Yep. So from a
You could
load,
use
in
that.
fact, if you have a high space, we'll make a rectangle, because rectangles are the best. There is what is it called? Windows up high, or they'll create geometries architecturally that on purpose draw heat in, so you can open windows and you pull air through the building, and that's called something. And I've done it for San Diego Community College District.
It's like an old, like a Roman strategy, right?
Mm-hmm. Yeah, yeah.
There's like a
it's an
Roman name
ancient.
for it or something?
It's an ancient technique, but the idea is, like Steven said, and you got lots of money if you're building a building this tall, but we're not standing up here. This could be 120 degrees, right? But if we make this hot, which I guess is how I could start this, things go from cold to hot, right? Hot air rises. So this creates, it's a natural ventilation technique, I guess. Where we also use that too, so general load calc methodologies, which we'll talk about next week. We use a mixed space. For higher spaces, we look at stratification, which means we would view the 6 feet that people are in different than the 20 feet up in the air. And so we look at high lobbies and stuff like that differently. From a code compliance standpoint though, I don't know if you can make that case. I think we're just gonna, let's keep going. Okay.
I have a question.
Yes.
Like, won't we use that design for like all types of buildings, just to release like the heat and attic? Or like,
We kind of do. So homes have
oh yeah, those
whirlybirds.
yeah.
There's little things like this.
Mhm.
And now I'm
Okay.
gonna, yeah.
Yeah.
Oh.
Probably needs to be more in like buildings and stuff.
Yeah, I mean,
it kind of helps
it's
with the airflow.
it's
It's a big
costs.
thing.
It's this is a natural ventilation strategy. So for certain areas, natural ventilation is not desirable. Commercial office spaces. That's not true. There's a good amount of commercial office spaces that have operable doors and windows. Looking for Continental people. Continental's got a lot of stuff that opens out into patios and cuts out our air conditioning. Still code required to have mechanical units though, so don't let anybody VE or air conditioning out of it, even if you can open a window. Natural ventilation is not, you used to be allowed to do natural ventilation only, but now you're required to do mechanical too.
Look at Europe for the reason why.
What's that?
So you can look at Europe for the reason why
Yeah,
it's important still have the.
or maybe some sheet metal lobbyist, I don't know. But yeah,
But I mean, like looking at, I just mean, yeah, a place that has relied on natural ventilation a lot and
yep,
is struggling to keep up with.
yep. Or they're experiencing a
Yeah.
huge heat wave, and yeah, that's costing them. Yeah. Okay, so let's talk through the other stuff on here that we haven't covered. Okay, so partitions. We generally don't account for partition differences, or if it's indoors, it's even if we set the thermostat differently, we're not going to put that on a load. We're going to assume they're all going to be at a certain space. Though if you see something wildly different. You might want insulation, so if you have like a steam boiler room next to a critical temperature space, you might want to account for the load across that wall or ask for insulation. Ceilings are part of kind of the system selection and how we account for those. The biggest, and I drew this in a way that doesn't let me make this part, so I'm going to make a revision. If this wall goes up, some of this wall load is going to go to the ceiling space, and some of this wall load is going to go to the space. Generally, so what that means is we will calculate the airflow for this diffuser to cover this space and the wall load for this space. Practically, whether we do this or not is another discussion, or whether it really matters. But the airflow will be driven by the space, the return air temperature. If this is a VAV supply ceiling return, this return air temperature will get conditioned by this wall, and it won't require more air in this space. When I say conditioned, I mean it'll pick up heat from that wall. It won't require more air in the space, but instead of being 75, which is what the space return air temperature might be 76, 77. So there's ways to account for that depending how it exists and how it's in the load. Also, if that's there, now you've created heat transfer here, and it's okay, how granular do you want to get into this? Generally with room loads, not that much. We're going to get them about right. When it comes to air handlers and bigger pieces of equipment, then we might start thinking about these factors to solve for the big compressors, big chillers, big fans. But that's next week. It's not. Okay, so we got ceilings, we got partitions. Skylights are kind of like windows, but they're on the roof. Roofs are kind of like walls, but they have more requirements, like we talked about. Floors we generally ignore, but the ground temp there is heat transfer there. It's pretty negligible in Southern California. It might be a bigger deal elsewhere. What I usually point out at this section is if you have a parking garage under your floor, you cannot ignore it. That means interior zones are going to need heating typically, because there is a load if there's a parking garage in here. If it gets 40 in that parking garage, you're going to lose heat. If it's 100, that's much more bearable, but you'll also gain heat from the parking garage too. Infiltration. We generally don't account for infiltration. And here's how we deal with that is we positively pressurize our building so that the air goes out of the building. If we're sucking air into the building and we want to account for that, we have a bigger problem. We don't want air coming into our building unless we're controlling it through our outside air damper on the air handler. That doesn't mean you might not need a fly fan for a kitchen, or you might need a vestibule for certain spaces. There's practical ways to deal with air filtration, but from a load standpoint, that's not usually a big factor. I'm sure you can come up with an example where it does. I can't think of one right now. Also, infiltration, when we talk about sizing humidifiers, we think a lot about infiltration. Or even all these assemblies we talked about, there's an aspect of vapor barrier where water goes in or out of the building, depending if there's something to block it or not. And that's another big infiltration discussion that is not covered in this course. Okay, I think I'm going to stop there. Yep, perfect time to stop. But next week we will talk about, no, let's cover heat loads because it's really, really easy. Heat loads are just like cooling loads. And we may talk a little bit more about this next week, but we don't have people, lights, or equipment. And the heat goes out instead of in. So instead of being 90 outside, it's 40. Generally, heating does not drive our market. Generally, we do a lot of rule of thumb type stuff with the move towards decarbonization in our market. It's costing a lot of money, so we will probably be spending more time thinking about heating loads. So I've seen a handful of presentations that rule of thumb heating is generally 10 to 15 BTUs per square foot. And that's a good place to start if we're pricing something up. Engineers have done a lot of studies saying it's at least half of that in practice. And we can get more aggressive with our designs. But the load calc software that exists generally supports the 10 to 15 BTUs a square foot. So it'll be interesting because the solutions for heating have gone up in price, in my opinion, tenfold, at least with the new technologies. So that's a rant that I won't do right now because you guys all want to get back to work or get another slice of pizza. Next time we will talk about some practical load calc procedures and estimates. I'm thinking like CFM per square foot, CFM per mullion, BTUs per square foot. I know a lot of the PMs are using it for estimating stuff, so I'd love to have that conversation. So come ready with that. Looking at you, looking at a few of you PMs. And then I want to talk through system level factors, block load, diversity, safety factors, software. There's lots of different softwares to do this, and then equipment selection. How do we turn this into something we can give a vendor and buy something? Because that's interesting, and there's a lot of there's different ways to do that. So, and I want to lean in and tell you how we should be doing it. So that's all I got for today. Thanks for coming. And if you have questions, ask me next week. Yeah. Or not right now. I don't hold anybody here for it. You can ask me one-on-one right now.
I think I have like some sort of solution for how I think like as a society we could reduce energy.
We don't handle society problems here. Yeah.
Well, I'm saying
I'm
like
just
I
messing with
think
you.
we should do more of this stuff
Mhm.
rather than this stuff.
Mm-hmm.
Because
Yep.
it's like over here we're trying to build a building that kind of operates within the climate that it's in
Mhm.
more efficiently with like less loads and energy use.
Yep. Thermal chimney, I think is what this is called. Yeah.
Okay.
Man, I needed that like 10 minutes ago.
Yeah, I'm sure there's like a name for that process because
Yeah.
it's like an ancient thing that I've seen that's been
And
popping up.
and it's
Yeah.
I've done one building that's done something that drastic because we had like a 2-story lobby space and we built like 15 feet taller.
So yeah, what I'm saying is like I think like buildings should be built more like this because
Mhm.
this like operates within the climate like a more like in unison.
Mhm.
And like over here we're trying to build our own microclimates and trying to like
Yep.
reduce energy as much as possible. But that's only because we all want to live like right next to each other.
Yep.
And like all the walls and like all the houses, and that's why we're creating all these heat islands.
Yep.
Basically, is because everyone wants to do the same thing. And like if we try to move towards this, we wouldn't be able to live as close to each other because like we would need more real estate to kind of get that airflow
Yep.
to go through the buildings. That's why I think we're not doing this as much anymore.
Well-
so that kind of answers my question about
So
why
so
I would ask you.
a lot of
basically.
discussion happens in the AE space about like biomimicry
Yeah.
and like doing things the way the world was designed, right?
Right,
Like
right,
taking
yeah.
advantage
Yeah.
of, like, and some of that can be done naturally, and some of it, like, it's just hot, and so if you want to live in downtown LA, you're gonna need air
Yeah.
conditioning, right? So
Yeah.
yes, you could be spread out, but that's not how
That's not how.
the world works.
Yeah.
That doesn't mean we can't take
'Cause
stuff
it's gonna
like
help
this.
us, right, for energy, like
Yep.
as an energy standpoint, to save.
And
to
here,
save.
here's the other thing
So
is
we kind of have to think back to our roots, is
You-
like what I'm.
you can
thinking, yeah.
raise thermostats, you can rate, but do people tolerate that? Do people think that
Yeah.
way? Do people really care about saving energy?
Yeah.
And
This-
should we force them to do it,
Yeah.
right? And
Like this perfectly aligns with spectrum. Like this is the far end, and then that's
Yep.
another end also. So it's
Yep.
like we have to try to land like in the middle. Of
Yep.
Like, so that way we can operate more efficiently.
and this is a conversation I've
Yeah.
seen happen over the last 20 years.
Yeah, that's what
is-
I've been seeing popping up.
Yeah.
In like,
or this is happening. So,
yeah.
I
That's
mean,
what I was kinda
air
curious.
conditioning is new, right?
Yeah.
Or it's a pretty new invention.
Mhm.
So it's amazing that we can build boxes and like live
Mhm.
and work in them
Yeah.
and not like